Hello.
Hi.
Okay, I think we can begin. So today we'll be rounding up data description, so that next week we begin the introduction to probability theory. Now I'm going to share my screen, and then we can begin. So here we go. So now we start with, we round up with what we call Chebychev's theorem. Chebychev's. Now, on Wednesday, I showed you, we covered the empirical rule. And I mentioned that empirical rule, we use it for data sets that are approximately bell-shaped, or normal. So the question must mention that it is bell-shaped or normal before you can use empirical rule. But Chebyshev, we use it for any distribution. So if the question does not say it, assume that the data set is symmetric or normal. Then, in that case, if it doesn't say that, that means that you're going to use the Chebyshev theorem. Okay. So Chebyshev's, what is this saying? It says that for any data set lying or with K standard deviations, especially where K is greater than 1, basically that's where we use Chebyshev for any distributions, provided that K is bigger than 1. And what is K anyway? K is simply means the number of standard deviations. So at least 1 times 1 over K squared times 100% of data sets will lie, well, at least one of them will lie certain, distance. Or the best way to put it is this: the position of any data set lying within K standard deviation will be at least 1 minus 1 over K squared times 100%. So you use it to estimate the percentage where the data set will be, of data will be lying. So the percentage of the position or the place where data will be lying, we use the Chebyshev to estimate it. Now, because of this, we're talking about where it lies away from the mean. We can still use the first thing you do is to estimate what K is. And in general, we also use the standard deviation to express how far apart the data value is from the mean. So we can also use this part as well if we don't have enough information to estimate K, or when we have a different kind of information. Then we can use either this one to estimate K. There's another way we can estimate K. I'm going to show you the data sets. You can use it in this form. Let me take you to, give me 1 minute. Let me open the next workbook we'll be using. So now I'm going to take you there. So another way you can estimate K is to use this formula, formula here. It's called K equals, you can use upper end minus mean, where the mean is, you're going to use a symbol mu to represent mean. That is it, I think it's somewhere here. Let me see. Yep, right here, divided by the standard deviation, which is right here. Now, this is for the population. You can also use lower end minus the mean divided by the standard deviation. Either one, it will still give you the same results. So I'm going to paste it here. So lower end. So either way, I'll get the second one that involves using the lower end. The lower end, and put lower here. As the mean divided by standard deviation. Okay. See, both of them will give you the same results for K. Now, let's see how this works. Remember, first of all, you can use Chebyshev for any distribution that can only be stated for values of K that is greater than 1, unlike the empirical rule where you can use for only the symmetric distribution. Now, when solving problem that involve Chebyshev, that question will not mention anything about normality or symmetric or bell-shaped. If it doesn't mention that, that's how you know that you're going to use Chebyshev. Another thing is to use Chebyshev theory. First of all, estimate the K first. Find what K is, and then you can then plug it in the equation. Now let us see how this goes. Let's say find a question that involves Chebyshev here. This one says, past result from the National Health Survey suggests that pulse rates of women have a mean of 76 and a standard deviation of 12.6. Assume that the distribution is symmetric. Let me see, you say here, assume that the distribution is symmetric. This means that we can use Chebyshev here because it said this assumption of bell-shaped or symmetric is stated, so we can use it. Now this is the one I know, I'm sure I'll be okay. Right, look at this one here. It says, okay, the average number of checks at a local restaurant is $36.42 with a standard deviation of $8.15. What is the minimum percent of checks between $15.25 and $57.61? What is the minimum percentage of checks between this value? So it didn't say anything about assume that the distribution is normal or assume that the distribution is bell-shaped. It doesn't say that. So that means we're going to use Chebyshev. Solution. First of all, let us find it. The mean is, let me see. Yep, I think we're in the same page. Yep, the mean in such, the mean is $36.42. Okay. And the standard deviation is, okay, equals $8.15. Now, you say what minimum percentage of the checks are between these two amounts? So now the upper, the minimum, say, if you look at this, we say between $15.25 and $57.61. So that means that the lower, in this case, is $15.25 as the lower end. The upper end, I'm putting both of them because I want to show you that it doesn't matter whether you use the upper end formula or lower end formula. Upper end is $57.61. So now let us find the K. Remember, I said first thing is to find the K. We can use those formulas that I mentioned. So suppose we use this the first formula, which is the K upper end. Okay. This means that K equals The upper end is $57.61, 57.61 minus mean of $36, mean is 36.2 divided by standard deviation of $8.15. So when we put this in decimals, let me write it down so I can put them in decimals. I got 57.61 minus 36.42 divided by 8.15. So let's do it on decimals so you can see. I'll take you to decimals now, the free calculator. Okay, decimals. Okay. All right, I have here that's $57.61 minus $36.42 divided by $8.15 give us 2.6. So care is 2.6. Right? 2.6. Okay. Now I'm going to take you back. So our care is 2.6. That means 2.6 because care is the number of standard deviations. Care is not the standard deviation, but the number of standard deviation away. Now, as a check, we can even use the upper end. Remember, I told you you can use either or, either the lower end or the upper end. So as a check, we can use the lower end, just the left side to confirm it. So I copy it, and I put it right here, where we are. Okay, which means for our check, care is lower end here is 15.42, $15.25 minus the upper, minus the mean, which is $36.42. Okay, divided by the standard deviation of $8.15. Okay, which is, write it down, $15.25 minus $36.42 divided by $8.15. So that we have this as a check. Remember, I'll take you the decimals. So I'm put the lower end here, which is gonna be $15.25. See, it's giving negative 2.59, which is approximately negative 2.6. Okay, negative 2.59, which is approximately negative 2.6. So negative 2.6, negative 2.6. Remember, negative sign here is just to show you that it is on the left side. We're not worried about the negative, it's just to show you that it's on the left side. So you can see that whether you use the upper end or the lower end, you still get the same answer, 2.6 standard deviation away from the mean. This is 2.6 standard deviation away on the right side. This one is 2.6 standard deviation away from the mean on the left side. So now that we have care, we can now be able to answer the question. The question says, what percentage, what is the minimum percentage of the checks are between $15.25 and $57.61? Now that you have found the care, you can now use the formula for the Chebyshev. It said at least 1 minus 1 over k squared. You can see that at least 1 minus 1 over k squared times 100% will be the minimum percentage of check that will be between these two amounts. Will be changes to just for me. Let me correct this. Make it font 16 and Time New Roman. Okay. Okay. Will be between the minimum will be between the between these two amounts. Okay. Will be between $15.5 and $57.61. This means that since we have K 2.6, we plug it in to this formula. So at least we have 1 minus 1 over, I'll call it 1 over 1 minus 1 over K, 1 over our K is 2.6, 2.6 squared. 2.6 squared. Okay. The computer put this automatically. Let me take you to where the formula will allow us to put it in properly. At least. So let me take you to the second workbook, so where it will allow us to use the formula properly. At least I got 1 minus, okay, I'm gonna put it right here. 1 minus 1 over K squared, 1 over 2.6. Oh, okay, 2.6. Okay. 2.6 squared, okay, times 100%. Okay. Okay, now see, it allowed us here. So I'm going to take it back so we can paste it here for bigger, so you can see it more clearly. At least 1 minus 1 over 2.6%, 1 over 2.6 squared, okay, will be between $15.25 and $57.61. So now we can figure this out with this most calculator. So we give us that 1 minus 1 over 2.6, it's gonna be 1 divided by 2.6 squared. Now 2.6 squared from decimals would be I'll make you that 2.6 squared. Yeah, 2.6 squared is 6.76. 6.76, okay? 6.76. I'll take it back. What about 6.76 times 100%? See, which give us now having figured this out, we can now put everything in decimals and get our result. So now we have writing it down. Okay. 1 minus 1 over 2.6 squared times 100. So I will take you there. So we can now fix it, find out once and for all. So I will have clear out. Okay, 1 minus, okay, 1 over 2.6. Okay, squared. Hope you are seeing this. Yeah, good, we are seeing it. 2.6 squared times right here, 100. 85.2%. 85.2%. Okay. Which is 85.2%. So that means that at least interpretation. At least 85.2% of the checks at that restaurant are of the checks in that restaurant between $15.25 $15.55 and $57.61. That must be a very high-end restaurant, not too high-end, but at least you get the point. That's the most important thing. Any question for me? Any question for me?
No.
Okay. Now, so this is one way of using Chebyshev. Sometimes the question might ask you to fill up a table like this one. It says, yeah. So it says use Chebyshev theorem to complete the table to find the minimum percentage of data values that falls within K standard deviation of the mean. In this case, they gave you the value for K already. So they want you to calculate the percentage. Let me make it a little bit bigger. Okay. So they're asking to find the minimum percentage that will be here. So since the question already gave us the K, we're not going to worry about finding the K. So we just use the formula here, this one here, this one here to find the minimum percentage that we're looking for. Okay. So we're going to use it here. Now, let's see. The first one is a for K equals, first K was 1.5. So given that value for K, we can now get the rest. 1.5, okay, 1.5. That means we're gonna plug this in. Let me take you so we can plug it in. Okay, K 1.5 gonna be 1 minus 1.5. Oops. 1.5. 1.5 squared times 100%. So that from decimals, we can just plug in the 1.5 there. Put 1.5 here. It was 55.6%. So to here, 55.6%. 55.6%. I'm going to copy this so you can see like in a bigger form for our take you to our main workbook. So for K 1.5 is going to be 55.6%. Okay, 55.6%. See? Now for K 2.0, K equals 2.0. Again, you plug into the formula. So I'm gonna take you there in a minute. 2.0, we have this. Change this to 2.0. Times 100 give us 75%. So I'm going to take you to our second workbook, where we put 2.0 here. Okay, here, 2.0, and that will give us 75%. And then I'll put it on our main workbook, 75%. Okay. Here, adjust it. Now, 75% to be here. So it keep going on and on. Let's do one more example there, and I'll now complete the rest of them. For care equals, next one is 2.5. 2.5. Okay. I'll take it there in a minute. Excuse me. 2.5. So I go to Desmos, make it 2.5. 84%. So let's take it, adjust in this, in the other workbook. I think it's 84%, I think. Let me see. Yeah, 84%. So taking it to other workbook for 2.5. 5, and then 84%. 84%. Okay. The main workbook. So for this, we got 84%. Okay. So 84% for this one. So I following the same process. I calculated the rest of them. I think I have them here. Let me see. That is somewhere. That should be somewhere. Yep, 84%, 88.9%. Next one, 88.9%. 0.9%. And the last one is okay. The last one is 3.5. I got 92%. Okay. So that's basically, at least as far as we can go when it comes to Chebyshev theory. And remember, today is just a random conclusion of this data description. By Monday, I'll upload a new handout and a new PowerPoint for you. Of course, if you already have the Pearson account, you see there's going to be, you have access to the textbook there. Textbook is there already. But in any case, I'm going to upload a new handout for probability. And then we'll start working on that on Monday. So I'm not going to keep holding you for any longer today. Any question for me before we round up?
No.
Yeah. Well, don't go yet. Let me check your attendance. Here I got, okay, only 3 of you came. Okay. I got Aaron. I got Ania. I got Nick Colson. All right. You all have a good weekend.
You too. Thank you.
Well, bye-bye.